So, good morning and welcome to the live stream of the lecture Scientific Visualization. Today's topic will be filtering and mapping. So we got a lot of interesting things coming up and we're moving towards those topics that most people would actually consider visualization. Right? So I mentioned already that visualization is this whole pipeline process, whereas the rendering part, the image generation, is at the bottom, but we're sort of making progress towards that. In particular, the mapping stage will feel like rendering visualization already, even though it's just mapping data to renderable primitives, but we're getting there. Okay, so today, as it's called filtering mapping, I want to talk about, well, filtering and the mapping stage. Let's start with filtering. So what is filtering good for? Well, you can see from this view here that we transform raw data into the vis or in long visualization data. So we kind of figure out what are the parts that we're really interested in. So here's an example of a data set. So what you see here is a three-dimensional direct volume rendered image of a human hand. Or you rather don't see it. It's still a data set though. It's a data set of a computed tomography contrast agent human hand. It's actually a pretty high quality data set. However, I didn't properly filter it. So if I do more reasonable filtering operations on a dataset, the same dataset with the same rendering approach will result in these images here. So what we usually need to do is we need to remove some of the information, some of the data to, well, literally see what's going on inside. So filtering is really this reduction of displayed information. And there's a couple of ways how we can achieve that. And let's focus on some very prominent ways that we'll need throughout this lecture quite a number of times. The first one is the projection, where we basically, well, project the data. So we reduce the data by simply ignoring parts of it, projecting. You can imagine this as really a projection that you know from graphics, from just drawing, right? You draw a three-dimensional image and you remove the third dimension, for instance, by just ignoring it, by just considering any XYZ point just as an XY point and then plotting it, which will result in what we call orthographic projection. The other operation is selection, no? And that already from its name tells you, well, you select certain types of the data. Okay, so notice that there's different things, fundamentally different things going on here. So here we have some sort of an operator, some sort of a selection predicate that ignores part of the data. And on the other side, projection, we sort of ignore part of the domain, but only its domain properties. So it's, for instance, the z-coordinate, but we still consider every point. Let's look at projection first. It's generally referred to as pi. Greek for p, right? What we can do projection based on both the domain or the data values. And we project into a subspace. I already mentioned this idea of taking just three-dimensional data, ignoring the third dimension, and then, well, getting just x and y points on a plane. What you see here is a projection of a flower. It's, again, a computed tomography image, by the way. It's a computed tomography image of a rose. And that's what you get if you just project it. Here's another image of a peach. So you see the core and you see some whatever fluids inside that react differently. All those images were done by a colleague who works at a hospital and who from time to time hires the hospital. So he actually pays the hospital to scan some out of the ordinary objects. And then he generates images such as this one here from the data sets and sells those as art. So if you're interested, his artistic name is called Studio Frido. You can find him on the web and buy framed pictures of various objects that that he CT scanned. It's quite an interesting thing. Anyhow, what he does is he takes those objects and CT scans them, and then he gets a data set. And afterwards, well, it's a three-dimensional data set. So to get them back, you need to project them, right? Literally take the pixels in or the voxels in the three-dimensional volume and generate a two-dimensional image from that. So on the one hand, it's a projection. We ignore the z-coordinate. On the other hand, it's a selection because we also ignore a lot of values of the data set. Okay, so both things are happening here simultaneously. Instead of just taking fruits and flowers and putting them into CT scanners, you can also take other data as input, obviously. You can take other medical data, but here's an example just of a simulation data. So that's a methane flame burning, and it's a flame that gets injected from the left into a burning chamber, and then you see its development. Notice here I used color for a change. But this color doesn't represent or doesn't correspond to any like real world phenomena. So this here is a data set that is where every voxel contains temperature information. And I just applied a function that looked reasonable. So high temperatures I colored in purple, and then yellow, and then red. But this is just a visualization of a temperature data set. It's not something that you expect to see, right? I can't even remember the exact temperature, so it's probably very high temperature, so it's most likely invisible to the human eye anyhow. But nonetheless, you see, it's a three-dimensional data set that gets both selected and projected. So we kind of do both things simultaneously. Let's also quickly talk about the selection operator, sigma here. Again, it's just an S, so we call it sigma. And for that, I have a little bit more to say also from a mathematical point of view. So it's an operator that takes domain or data values into account and executes some function that pretty much says yes or no. It executes a predicate on that. And here I have such a predicate just as an example that combines both a domain and data values. Okay, so for instance, if I have a height field, which is just a set of x, y, values that map to a certain height. So it's a plane with height values. We would probably call this a height field or terrain. And say I'm interested in this predicate here. So my input is x, y, and height. And what I select out are those values. Let's start from the left here, where h, the height, is more than 1 kilometer. Okay. And where x and y, each squared, added together, where the root is below 5 kilometers. Okay, so that's just a mathematical term. What would that do? Well, it would filter out any mountain that is not more than 5 kilometers from the origin away. Okay, so you see that there's usually some sort of semantic to these functions. There's some meaning. We choose them for a reason, but we can also just express them mathematically. What we get in the end would be, well, a selection of these mountains, but those are x, y, and height. So in other words, x, y, z coordinates. And then we would still project them. So usually if we have anything that's beyond 2D, we need to project it onto a screen or a print or a piece of paper. So in general, you see a combination of the two. So that's just a very general description of what a selection is. Execute a predicate on the data and a domain, and you get some values out, and some are lost. Okay, so let's look at a few very prominent examples of selections, for instance. One prominent thing in particular for volumetric data sets for a selection operator is slicing. So we choose a set, either one or a set of two-dimensional planes usually, but they could be anything, but normally they're planes. So in this case, we choose a set of planes. Look at the hand data set again. And I've chosen 3 different planes. They're all orthogonal to each other in this example. They don't have to be, but they often are in practical application. And here you see what's going on those planes, on those 3 planes. Okay. Those planes, of course, do not have to be axis aligned, right? At the bottom, I have a plane that's just kind of cuts straight through. And as I said, they don't even have to be planar. We could choose any manifold and then map it back to a plane when we want to render it or project it. However, since ultimately humans are supposed to make sense of that, it's usually beneficial to keep the planes axis aligned and keep them planes to start with, because that makes mapping easier. And this here is the dominant visualization technique, for instance, in medical imaging. So even though 3-dimensional data sets are acquired on routine basis, CT, MR, PET, all of those modalities produce 3-dimensional data set, In most cases, doctors, practitioners look just at the two-dimensional slices of the three-dimensional data set. And the reason for that is it avoids occlusion, right? If you look at the hand, in full 3D, parts of it occlude other parts. Whereas in 2D, when you compute a slice, you don't need to project, right? So you see the full data set. There's still a selection going on. So for instance, we filter out the noise. Remember my hand data set in the beginning, which was just this brick. So we filter out noise from the surrounding air. But this filtering is much more intuitive to handle for people. Okay, so we say, okay, well, those are lower values. They can contribute to any reasonable human tissue, so we can remove those and let's color code the rest, say, for instance, in red and yellow here and white, and then just look at the slices one by one. And then what a lot of practitioners do, they kind of go through the slices quickly. So if you look over the shoulder of a doctor in a hospital or a radiologist, you see them kind of running through the slices back and forth, and then they reconstruct the full data set in their mind, which is occlusion free, so to say. Okay, and that's actually an interesting open question: is how can we design the 3D visualization so that this kind of going through and reconstruction like manually doesn't have to be executed anymore, because that's very error prone, right? Whenever there's some complicated three-dimensional structure, there's a lot of examples where in the clinical practice this kind of going back and forth and reconstructing it in your mind goes wrong. One particularly good examples are blood vessels. So blood vessels tend to kind of grow back and forth in 3D, and it's very hard if you just look at cross sections and all you get are cross sections of tubes, right? You get a bunch of circles, and reconstructing that is very hard. It requires a lot of practice, like decades of practice. And still mistakes happen. Okay, nonetheless, but that's slicing. Okay, another method for selection, which is seemingly very similar, but it's actually pretty different, is clipping. Okay, so here we again use a medical data set. I again use a plane, just one in this case, could be multiple, but I just use one, and I run this plane through the data set. But instead of taking the data that is just on the plane, I remove all the data, or in other words, I select all the data on the other side. Okay, I remove the data on one side and just select the data on the other side. Okay, so here's the visible human data set. I've set this clip plane. I've placed this clip plane right through the skull. And then what we can see here, this is the unclipped data set at the top. So this is what I would see if I would look perpendicular onto the plane. So I basically see the skull. If I now look at the clipped data set, I can selectively remove like half of the skull and then look inside. It's empty here. Why is it empty? Because this data set is a computed tomography data set. And what did I say about computed tomography? It's pretty good at distinguishing air from bone from anything else. Okay, if we want to see the bones, they are stuck beneath the anything else. Okay, so those are fat, muscle tissue, and any organs. So to even see the bones, I have to run another selection on top of this clipping selection here, and that removes, well, the anything else, and hence that includes any brain tissue. Okay, so CT without any contrast agent is just good for looking at anatomical, bone anatomical structures. Okay, but nonetheless, there might be fractures or so that you're interested in. So we now have selection and projection, and all the while I mentioned this, like I remove parts of the data here on top of it, right? So that's what I said a couple of times. Let's look at that particular process. How do I get rid of the air? How do I get rid of the bones? How do I get rid, well, if I want to, how do I get rid of the soft tissue? And how do I color those tissues on top of that? Okay, so in that selection is generally done by a concept called a transfer function. So this transfer function is a very important process, and again, both in the clinical practice as well as in pretty much any other regime where we use a volume visualization, the transfer function is the most important selection metric. Okay, so here again, the hand data set, it's the same data set on the left and the right. I just used a different transfer function. I just used a different means of selecting data out. The transfer function works only on the data values. Okay, it doesn't work on the domain. It doesn't care about where in the domain I am. At least not if I just use it as it is and do not combine it with any other method. Okay, so what you can see here at the bottom are two different transfer functions. So let's focus on this transfer function here. What you can see is, you see a two-dimensional image. In the background, you can see what's called a histogram. A histogram is a statistical analysis of the data set. I'll have a little bit more about histograms later on, but just here as a quick intro, a histogram is a bar chart, pretty much, that it tells me for each value, so what you see on the x-axis are the values from, say, 0 to 1. For a CT scan, those would be the Hounsfield absorption values. Okay, so from 0 to 1, this tells me, okay, how many values with a low how many voxels with a low Hounsfield unit do I have? A ton. That's the air around the data set. And then there's way fewer values with this Hounsfield units. Apparently we have a peak here, so a ton of values have, or more values have these, have that specific value. Say it's 0.4, and then it decreases until it drops to 0. So that's the histogram. It gives me an overview of which values are present in my data set and how many of those, how many voxels do have that value. So the transfer function itself is this small graph here, or it's actually a number of graphs. And the only one that I'm interested here right now is the white one. Okay, so that's this one here. So underneath that, there's also a green, red, and blue. And those are responsible for the colors, which I don't really care about much at the moment. We'll have much more on transfer functions when I talk about volume visualization. Right now, I'm only interested in the white one. So notice that the white graph, it's pretty much 0 here, and then it increases to 1, so that's generally normalized. And it starts about here, sort of way after this peak. Okay, so this is where it goes up. And what this function tells us, this white function here, this is the selection whether we want to see a certain value or not. If it's 0, we say no. If it's 1, we say yes. And in between, well, there's also possibilities, and that tells us how much we want to see of that particular value. So for instance, if it's 0.5, it should be semi-transparent, so half transparent. If it's 0.9, it should be 90% opaque and 10% transparent. Okay? So this is to avoid hard cuts. So what we can see here, that apparently this function here filters away anything except the bones. Right? All I see are bones. So all of these values here that are underneath the ones must be bone, and anything else in front is not bone. So let's look at this function here and particularly compare again this white graph. What you can see is it's slightly shifted to the left. Okay, so here this starts underneath that peak, whereas the one on the right starts a little bit more towards the right. So what this means is, in this visualization, I consider more values. More values are mapped to 1. I consider more values. I select out more values, in particular those with a slightly lower Hounsfield unit. In particular, that slightly lower Hounsfield unit seems to appear pretty often, right? I mean, we got a peak here. So what is around here? So this is where all the soft tissue is located, right? So this is where muscles are located. This is where vessels in this case are located, because we injected, in this case, a contrast agent. So in the vessels, we also have a unusually high Hounsfield unit wherever blood is flowing. So by moving this towards the right, towards the left, we see more, well, literally vessels here. We see the blood vessels. Okay, if I would move this even further to the right, in particular, if I would include this one here, I would again get this brick data set at the beginning. Okay, so that's the transfer function, and generally you can change this here interactively. So as a scientist, as a doctor, you can move this transfer function around, and you can focus on different areas. As I mentioned before, when I talked about CT, medical practitioners call this process windowing. Okay, but it's really just moving around a function. They just, for some reason, decided to call it a window through which they look. Okay, so now we got projection covered, we got selection covered. And again, the idea of both operations is to get rid of parts of the data or the domain to get a better insight. notice that those operations, they all can be somewhat dangerous if applied the wrong way, because if I, for instance, apply this selection here, then, well, I don't see the vessels, sort of by design. But what if there's something unusual in the vessel, some sort of cancer that shows up because of vessels are making awkward twists? Okay, so when you do this, you need to be aware that you throw away data, and throwing away data might always include throwing away important data. So selection is very helpful, projection as well, but it's also a lossy process and it needs to be well thought of. And the best approach is if it's possible to do the selection interactively, meaning that if it's very fast, if the computation is fast, if the update of the images of the visualization is fast, we can just let the scientists, if they don't have a clue what they're looking for, and this happens pretty often, not because they don't have an idea what's going on, so they generally have some sort of idea, that's why there's domain specialists, but if they encounter a new problem, they might not have the exact idea what's going on, or they might be looking for something, searching for something, right? In that case, it's very useful when they can do interactive operations, so they can literally play around with the data set and, well, explore it. Okay? So that's selection and projection. Now, what we can also do is we can do filtering. Filtering is another operation where we do a pre-process. So this generally happens before the mapping and the rendering. So that's what I generally refer to as pre-process. We do a pre-process to, well, remove some unwanted artifacts in the data. For instance, high frequency fluctuations, also referred to as noise in general. Right? We want to remove noise. And one very prominent way to reduce noise is by the means of convolution. So I don't want to go into too much details about convolution and general image processing, as this is part of Professor Pauli's lecture. So if you attend Professor Pauli's lecture, he'll give you a much more sophisticated insight into image processing. But as you can see here, and that's an interesting insight as well, is that image processing, which I also always refer to as kind of the opposite process what we do, right? We generally take data and turn it into images, whereas image processing generally takes images and turns them into data. However, in visualization, if it's not just computer graphics in terms of effects or whatever, in visualization, we're kind of stuck in the middle, right? We start from data, which we could refer to as images. We do something with them, and then we visualize them again. So we're kind of borrowing a couple of techniques from the image processing community here. So then one is the convolution, right? Convolution is the star operator that I mentioned here at the top, and it's this integral thing. It's this multiplication of two functions, whereas one depends on sort of a center value and the other one not. But the intuition here, and that's why I've got this animation going back and forth behind me all the time, is that you can imagine convolution as sliding one function over the other. So here you can see how one function slides across the other function, and the result that I store is the product of the two functions, or it's the area underneath the function, or it's simply the integral, which is kind of the same thing. And that's depicted here in this animation as this blue area. If we're not dealing with continuous data, which we rarely are, we usually deal with discrete data, all of those scary integrals turn into sums. Okay, an integral is nothing but an infinite sum, but that tends to scare a couple of people. Well, it's just because it's an integral, sounds complicated. Think about all those integrals as sums. And what we've got here, we got two integrals now, twice as scary. And we got two sums, not as scary as the integrals. Why do we suddenly have two? Well, because we generally deal with two-dimensional data when we talk just about images. And then we need to go along x and y or u and v axis, or whatever you want to call them. We can also do the whole process in 3D if you think about the volumes. If we want to convolve a volumetric data set with a filter, for instance, a low-pass filter, one that removes noise, you would get 3 scary integrals and 3 sum. But still, it's in the implementation, and if you attend the exercise, which I again highly recommend, you'll implement some of those convolution, and you'll see that in practice, it's actually that simple. It's really just, for 2D data set, it's really just 2 loops that you execute over an array, and you just sum up a few things. So it's a that simple idea, but the best way to kind of grasp it is to go and implement it yourself. Okay, and depending on how I choose the filter kernel for those convolutions, I can achieve a different effect. Okay, so overall, as I said, it's a pretty simple thing. So we just slide this kernel, this filtering kernel, over the image. So we kind of place it at one point. In particular, if it's discrete, it's very easy to imagine. It's just a grid that we place on top of another grid, and then we just kind of look through all the overlapping grid cells, multiply the values, and then sum them all up. Okay, so it's really straightforward. Let's look at an example to make it even more clear. Let's say I just want to compute the mean. So I just want to take a pixel, take its surrounding pixel, and just compute the mean of the pixel in the center and its surrounding values. Okay, this way I smooth things out. Okay, pretty easy. So here's my filter kernel. It has 9 entries, and each of those is 1/9. So the sum is 1, and that's generally a good idea for a filter to sum up to 1. So what it does is, if I put that on top of 1 pixel, I'll just end up taking the average of its pixel and its 8 neighbors. If I run this on an image here with a relatively big filter, so that's not a 3x3, it's a significantly bigger filter to enhance the result, but the idea is the same, right? I get the input image, and then I get as output, I get this mean filtered, averaged out image, which is blurrier. And it has this, since I've used a giant quadratic filter, it does have this quadratic filter property in it, right? You can probably notice that it's sort of bricky. It has this axis aligned look, which I would consider an artifact of the filter, because there isn't like this axis alignment in the input image itself. Just as a side note, because I talked about a mean filter, there's another term from statistics that is very close, that is median. Okay, mean and median. Mean is just the average value, expected value, whatever you want to call it. Okay, that's the mean. The median is, and that's important, it's not a convolution. The median is, if you take a bunch of values and you sort them, you pick the center. Okay, which creates a similar effect. It also sort of smoothes things out. Why does it sort of smooth things out? Because any extreme value in the image, in the data set, will always end up being either far at the front or far at the back, so we never pick it. So we tend to pick values that are sort of, well, in the middle, right? It does have a bunch of advantages and disadvantages. Well, one prominent disadvantage is that it requires sorting. Sorting is a pretty expensive operation. It's n log n usually, whereas the filter, it's a convolution, it's just linear. And we can even get it to sublinear with separable filters. More on that in a second. So we generally have to do a little bit more work, and it's a very different pipeline because, again, it requires a sorting step. The advantage is it doesn't introduce new values. Okay, so if I compute the median from before, I sum up 9 values in my example, and then I divide the result by 9. So the resulting number could be something that wasn't in the original data set, right? For instance, if you start with a bunch of integers, since I divide by 9, it's very likely that I get some fractional number. Here, that can't happen. So that's a big advantage of a median filter. And here is also my previous example here. So that's the image from before, now median filtered. Okay. So what you can see, again, it's sort of blurry, right? Outliers are removed. I think it's most obvious here if you look at that palm tree, right? The entire trunk is gone. Why? Because compared to my filter, the trunk is relatively small. So it's an outlier in that area. So it just gets filtered away. And this is also what median is generally used for. It's for specific types of noise. So for instance, here, that's obviously an X-ray image of, I guess, the right human, hence the R. And if I add noise to that, so I add just speckles to that, could be dust, could be interference, right? If you would have taken an X-ray image anywhere near Chernobyl a couple of years ago, you would have created images such as this one here. Or just a photograph. It wouldn't have even taken an X-ray image. A photograph's just fine. That also gets influenced by radioactive radiation. So what you get are these spots, and to remove these spots, so all of these spots are outliers. So they are different from the environment. So if I just do a median filter, what you can see is it's not that much blurrier, right? If you particularly look at the text here, even though it's probably not really legible in both cases, but you can tell that it's only slightly less legible here, whereas those speckles are completely gone. Okay? But again, median is a nice operation. It's a very useful operation for certain types of noise, but it's not a convolution, very important thing. Now back to convolutions. What else can we do? I mentioned before, if I do this mean filter, it does have this advantage that it creates this blocky appearance, right? What would be better if we would have a more like a spherical filter, right? A filter that falls off in a spherical fashion. And fall off is really the key here. So instead of weighting everything in this filter region the same, I can also weight things in the center with a higher value, and then towards the periphery, give the values less influence. Okay? And I can do this any way I want, but as statistics has shown, as mathematics has shown, a Gaussian function is a pretty useful approach here. So for instance, in 2D, if I choose a 2D Gaussian and then here I discretize that, I get these values. I normalize this in the end, so if I take all of the numbers here and sum them up, I get 115, so that's what the 115 in front of it means. So I divide everything by 115 to, again, get it to normalized state. If I now plug that filter, that convolution filter, onto each pixel of my input image and check the products of the filter value with the image, then sum it all up, divide it by 115, I, for instance, get this image here for my example. Yeah, and here's a comparison of the box filtered, the Gaussian filter, and the median filter image. So they're all reduced in high frequencies. Okay, so any like small details are gone, but they're gone in different ways. Okay, and which one is the most suitable for your application? Well, it highly depends on the application, but they're all intended to remove detail. Okay, just as a side note, and again, all of this is discussed in much detail with a mathematical implication, with a statistical comparison in Professor Pauli's lecture. So if you're interested in that, again, attend his lecture on image processing. Okay, so, but just as one side note, because we will use those filters pretty often later on, and it's just important to know that there are certain filters that are called separable. So what this means is that instead of doing the 2D filter, which is only linear in complexity, meaning that I only look at a linear number of pixels, but then the image is in 2D, you could also say, well, it's a square, so overall the image itself scales quadratically. Okay, and to speed things up, what you can do is you can just do one filter in 1D. So instead of doing the complete 2D thing with linear separable filters, you can just do one filter in one direction, another filter in the other direction, and execute those one after the other, and you get the same result. Okay, so this is, in particular for large filters, significantly more efficient. And whoop, oh, drop clicker. So as you can see here, for a relatively small filter, which has 25 values, it's a significant reduction in data size. Okay, you can just do the math, right? 25, 5 by 5 is 25, right? 5 plus 5 is roughly 10, so it's half the work. And since one scales linear, the other quadratic, it only gets better with bigger filters. Okay, so that's just a side note. When you see some of our implementation, maybe later in the exercises, you might be surprised why we do a sequence of 1D filters instead of the 2D filter, and the reason is performance. Okay, what else can you do? In particular, when you do the Gaussian filter, there's one nice thing in the Gaussian, and that's the sigma. Okay, so you can tune the sigma to make this Gaussian like narrower or wider. And this allows you to, well, tune how much filtering you want. If the filter is extremely narrow, like taking only the center into account, small sigma, you get, well, only medium filtering. If you increase the sigma, it gets more and more blurry. Okay? Is this beneficial? Well, here in this case, it probably gets rid of reasonable data, but if I use, for instance, a noisy input image, and again, there's different types of noise, noisy input image, I choose the sigma appropriately, I can choose it to some level where the loss in detail of the actual signal is still acceptable, but the noise is gone. Okay, and here we have the situation. So noise is pretty much gone. Of course, there's also some detail loss, but that might be acceptable for my analysis step that I intend to do. And of course, you can do the same thing in 3D as well. So in general, we're most often interested here in at least three-dimensional data, and there's nothing wrong with doing the filtering process in 3D. So here's an artificial data set, here's a scanned data set of a lobster. So on the left, you have the original data, on the right, you have this filtered data. So you see that in particular, some of the artifacts from the slices, they vanish. And here's a more realistic data set in terms of it being an actual scan. Again, a contrast agent CT scan. See on the left, artifact, on the right, this noise is gone. Also, some detail is gone. But if we know the noise level of the acquisition, right, and that again brings me back to my argument from before, we need to know a little bit about what's going on, where's the data set from, how was it acquired, what were the properties of the acquired data set. If we know that certain frequencies can only be from noise, we should filter those out, and that's what a smoothing filter is good for, or a low-pass filter. Okay, why is it called low-pass filter? Because it lets low frequency pass and removes high frequencies, hence low pass. If there's low pass, there's also high pass. So sometimes we have situations where we are interested in boosting high frequencies. Okay, so for instance, we might be interested in to see the noise, like where's the noise coming from, right? But that's a very rare case. Often we're interested when I say high pass, we're interested in edges. What's an edge? Well, it's a high frequency, right? The signal changes significantly. An interface between two objects, between two tissue types, is something that we should potentially highlight in a three-dimensional data set, 2D, whatever. Okay, so how do we highlight edges? Okay, again, I'll just quickly run through this. You know where to find lectures on image processing, but just the two most prominent and two most basic operators to figure out edges. So the first one is the Sobel operator, and it's based on gradient computation. So what's a gradient? Gradient is a derivative. I already talked about derivatives in a simulation lecture a lot. In particular, I talked about an approximation for derivatives, the finite differences. And the Sobel operator is nothing but a finite difference operator. So what we do is we do two filters, one in X and one in Y. And let's just look at the Y filter here. Okay, so in this case, it's a 3x3 filter. And let's just look at the first column here. So never mind the other column, they're the same anyhow, right? So the like from, let's do it this way. So first, second, third, let's look at the third. So the first and third are the same, and the one in the center is also the same, just weighted by 2. Okay, so we can focus on this one. What does this mean? It's got 1 and -1 in it, so that's interesting. It's got negative values, and it's got a 0 in the center. What that means is if you just apply that filter, just the one here on the right, if you apply that to a one-dimensional signal, what would it do? Well, what would I compute? What would the result of this convolution, this magical integral thing, what would that be, right? If you forget about all the complexity, what you end up doing is nothing but take the point in question and ignore it. Okay, I multiply it by 0. Then take the bottom neighbor and multiply it by -1. Take the top neighbor and multiply it by 1. And what do we do then? Well, we add the two together. Okay, so let's sum this all up. What we do is we take the bottom neighbor, top neighbor, 1 times -1, the other times 1, which is just saying subtract the bottom from the top. Okay, and then since we generally want to normalize, we divide by 2. So subtract bottom from top and divide by 2. Does that look familiar? Well, that's just the center difference. Okay, so if you go back through the streams, you'll see that is the center difference. Those are that's the approximation of the derivative. Okay, and I went through a little bit more details, right? So that's basically the first von Neumann term of the Taylor series, right? So long story short, this is just computing the difference quotient. Okay, that's just a derivative. Okay, so we do this apparently in Y, and we do the same thing in X here. So we just basically compute the X and Y derivatives. That's it. Okay, so what do we get when we run this on an image? Here is the result. So if I take the left image, this person in front of a mirror applying makeup, I get this here as a result. Okay, so notice that the values can be negative, so I just use the absolute value here. So what do we get? Well, in areas that are pretty smoothish, right? So I get very few values, and edges are, well, highlight. So apparently highlight edges, I apparently highlight changes. What I also highlight though is noise. Okay, why? Well, because noise is usually a high frequency signal. It doesn't have to be, we could also have low frequency noise, but generally in images we have pretty high frequency, so we have pixel fluctuations. Okay, and you can see that, right? So if you look closely here in that area, there are some values that are still left, which are certainly not edges. Also on the face, if you look at the cheek, right? So there's also some some data left there. Like there are non-zero values at the arm as well. So the edges are highlighted nicely, but there's also stuff here, which, well, you might say those are actually edges. Those are actually vessels on the skin or hair. So you might consider them edges, but nonetheless, you see that noise has a significant influence on that. And that brings me to the Kenny edge detector, which is a very prominent edge detector that is built on the Sobel operator. And the idea is pretty simple. So it's comprised of 5 steps. And the first 2 is get rid of noise first. So we first remove noise by, well, Gaussian filtering. Just talked about that. Then we do the Sobel operation to highlight edges or to compute the gradients. Right? And wherever gradients are, there should be edges. Okay. And then we do a few more steps. So let's look at those in a practical example. Okay, so if this is our input Lena image at the top, at the bottom left you see the smooth version, so noise has been filtered out. A little bit of detail is lost, right? You see it's somewhat smoother. It might be hard to spot, but there's a little bit of detail lost. But in particular, those speckles are gone that cause trouble. Then I compute the vertical and horizontal derivative. And notice here that since the values can be positive or negative, I biased them. So for visualization purposes, I made 0 gray, and anything that's smaller than 0, between 0 and -1, I made that from gray to black, and anything above that was from gray to white, so that we can see positive and negative values better. Okay, hence the 0 level is gray now in this image. Okay, so this is always a problem. If you have negative values in a data set, how do you visualize them, right? You could do absolute values, and here I've chosen to bias the result. So now that I've got these edges, what can we do next? We can compute the norm. So basically I take those values here, the horizontal and vertical derivative, and combine them. So 2 values make up a vector. I can compute the length of that vector, and that's the norm. This is the norm of the grain. This is the length. This is a quantity that tells me, okay, how much of an edge is there, okay? And then I do thresholding. So next thing is I say, well, okay, anything below a threshold is probably like a rather smooth edge, which is not really an edge, or it's maybe still some leftover noise. So next step is thresholding. So I ignore all values below a certain value. It's a selection operator, by the way. You could do this by the means of a transfer function. And then I do thinning, which is just a tracing process along those rays, along those remaining edges, which are rays in a sense, and I get geometry out. So this is the final output. Geometry, the top is just a pixel grid, so those are really vertices and edges, so that's a graph here. Okay? And it gives me an edge representation of the original image. Not perfect, but it's pretty good, and it's relatively simple to implement. So that's the Sobel operator as being part of the Kenny edge detector. Okay, just like the Gaussian filter. Okay, another prominent one, just to mention in a second, very prominent, very basic, very simple edge detection operator. That's the Laplace of a Gaussian, or LOG. Okay, it's not the logarithm, it's spelled a little bit different with upper and lower case, but it's Laplace of a Gaussian. And the idea here is not to look at the first derivative, as we did with Kenny edge detector, but to look at the second derivative. Okay, and why do we care about the second derivative? In particular, we care about the zero crossing of the second derivative, and we call that an edge. And previously, we also did a Gaussian smoothing, hence the Laplace of a Gaussian. So taking the signal, applying a Gaussian to it, applying the Laplacian to it, looking at the zero crossings. So in essence, to name this a little bit different, we look at the places where the second derivative of the smooth image is 0. Why should that be an edge? Okay, the answer is pretty simple. So let's look at a function, okay? Let's look at the function. So the topmost function is our image. What is an edge? Well, an edge is a change. It's a relatively rapid change from one value to another, right? So if I just look at one line in an image, I have 0, and then I have 1, and in between I have this relatively rapid jump, and that's what we call edge. Now, since it's generally discretized in some way, it's not necessarily just a one-point edge, so it might be a little bit smooth. But where is the edge then? Well, I would say the edge is probably in the center. Okay, so that's the most reasonable way if I don't have any other idea to place the edge. Okay, let's look at the first derivative here. That's what we did so far. And as we can see, the first derivative has a peak here. Okay, it's got a peak there. And that's what we used before when we ran the Sobel operator, right? So we would do this computation here, at least, or a discretized version thereof. And we would then say, okay, well, wherever that thing is big, we threshold it. Where it's super big, we take it, and those are our edges. Okay. What we can also do, we can try to find these places here, and that's what's called an extremal point. How do we find an extremal point? Well, we compute the derivative and look at the zero crossing. Well, that's just high school calculus, right? So we compute the derivative of the derivative, which is also referred to as the second derivative, and we look at the zero crossing of that one. Okay. So that's just about it. That's the reason why we consider zero crossings, so places in the second derivative where it's 0, to be a good metric of an edge. Okay? The trouble is, again, this is very sensitive, and the second derivative, even more than the first, is very sensitive to noise. So if there's noise in there, you get crazy second derivatives. You get a ton of zero crossing, so it would be pretty useless. Hence, we try to get rid of noise, and one way of getting rid of noise is just to compute a Gaussian filter first, to filter out high frequencies. Okay, and that also is the reason why an edge is a somewhat smoother thing. Now, the cool thing about convolutions is that we can fold them together, right? Instead of doing one convolution after the other, we can just multiply the convolutions together, because it's all just sums and multiplications. If you do this properly, you can just multiply the convolutions together to get one single convolution out. And that's exactly this Laplace of a Gaussian. So we first compute the Gaussian, right? That's the fancy, that's the reason why we have an exponent function in there, because the Gaussian function is an exponential function, right? And then we compute the second derivative of that. And what you get is a function that looks like the one on the left. And here's a discretized version of that one. Now, all you have to do is, if you have your input signal, you convolve it with that one single function here. And then you'll look at the zero crossings. So here's an example, again, the makeup application in front of a window. So on the left, you see the Laplace of a Gaussian, and you see it's again biased. It can be negative or positive. I biased it. So if we now look at the zero crossings, that's what we get. So it's again highlighting edges, but you can see there's still a ton of noise in there, right? You still see that there's apparently edges pretty much all over the place. So we might want to increase the signal. We might want to increase the part of the Laplace of a Gaussian that is the Gaussian. We might want to increase the filtering radius, so to say. Okay, it's not really the filtering radius. It's the shape of the Gaussian, but it takes more and more values reasonably into account. So if I increase sigma to 2, voila. You can see how a lot of that noise is gone, and we get a pretty nice representation as well for the edges. Okay. Compare that to the Kenny edge detector, and you get a similar result. It's not the same, but it's similar, and both are relatively easy to implement. Okay, so the difference is, again, Kenny edge outputs geometry, whereas the Laplace of a Gaussian outputs a grid, and one might be more useful than the other in different situations. Okay, but nonetheless, that's a way how to detect edges, and it trivially extends to 3D, right? So instead of doing this for 1 and 2, those are just convolutions, right? Just 1 dimension, 2 dimension. We just use essentially a cube that we slide over the entire data set. And with that, we can highlight, for instance, interfaces in tissue. And as I said, this is just the beginning, right? That's just the beginning of filtering. There's much more interesting filters, bilateral filters, filters that use different smoothings depending on local properties. So for instance, local derivatives. Here's an example of such a filter as it's used in medical imaging, which is a filter that takes curvature into account and smoothes out areas where the curvature is low with a larger sigma. And if I just apply that to a MR dataset, that's a slice through a magnetic resonance image, you can see that even if I apply the filter multiple times, like literally 100 times, not all the information is gone. It just smoothes out areas where not much is going on anyhow, but it retains the interface regions. Okay, so this is probably going a little bit over the top in terms of data loss, but you can see it's super smooth, and still the major features are in existence. So, so I said, in reality, we often use more complicated filters, but they might be very specific to a certain purpose. So it doesn't make much sense to talk about them in general. Okay, any questions at this point? So chat is working, thanks. Thanks for the message. So I now know that you could answer a question if you want to. Okay, doesn't seem to be the case. So then if you're still typing, go ahead, type, and I'll just stop. As soon as I see a question, I'll just stop. And in general, anyone joining in, feel free. I mean, that's the whole point of doing this live. The whole point is that you can ask questions, right? I might just record this ahead of times, get rid of all those blobbers when I drop the clicker, or when I don't know, have to drink or whatever. I could cut all that out. So there's a specific reasons for doing this live. That is for you to ask questions. So please take that opportunity. Okay. So let's, with that, kind of stop here as far as filtering goes. I think I covered, or I'm pretty sure I covered the most important filtering techniques as we will need them. And then as we need more during the upcoming topics, I'll talk about those in more detail whenever necessary. Okay, let's look at a mapping technique now. Now, what is mapping? We'll deal with the rest during the rest of the stream, during the rest of the semester. I'll talk about mapping and rendering techniques. So this won't be the last time to talk about mapping, but it's a very important thing. So what does mapping do? It takes the data, right? It takes the numbers and turns those numbers into something that I can draw, that I can render, or that a computer can draw and render, right? I can't really render 5. Right? I can't really render the sequence of, I don't know, the Fibonacci numbers, right? I could render them as digits, but that wouldn't help much, right? So I first need to turn those numbers, that data, I need to turn that into something that has a visual meaning, right? 5 doesn't have a visual meaning by itself. It's just an abstract idea, right? I mean, I could draw it as a 5, but again, that's already a visualization of the abstract idea. Right. So, but when I say, well, anything lower than 10, make this red, anything bigger than 10, make it green, and then draw it as a point, like a circle or something, that is a visual representation. And that's exactly what mapping does. It takes the numbers and turns it into something that has a meaning, which is usually a position, a color, shape, stuff like that. Okay. And what do we use for this? Well, points, lines, surfaces, usually made up of triangles, volumes, whatever. Okay, so that's mapping. Okay, good. So how do we do this mapping thing? And it's again very, well, it's somewhat specific, not very, but it's somewhat specific to the data, of course. I mean, if I have 1D data, I'd probably represent it differently than 3D data. I'll map it to a different primitive. And when we do this, we have to take all kinds of things into account: occlusion, colors in general, how color perception, human visual system, and that includes stuff like psychology. Okay, I've put this image up here during the intro. Maybe some of you remember, so that background knowledge might influence our perception of color or our perception of data in general. Our cultural background might have an influence on how we perceive colors. So generally, whether red is a good color for stop and green is a good color for go, totally depends on your culture. So there's a lot of things involved, and I don't want to go into those into too much detail, right? It's an interesting topic, but I'm not a psychologist, so you might want to refer to an art or psychology lecture. They spend a lot of time evaluating these issues. But just as a side note, we should take that into account, at least borrow the ideas, borrow the results from other domains to design a successful visualization. So for the most part, I'll ignore colors here because they tend to cause all kinds of issues, right? So I'll just dodge that problem by ignoring it. Okay, so let's focus on shape a little bit. Shape is a little less tricky when it comes in particular to psychological implications. Okay, so it's not completely free of any implications, but it's not that tricky. So let's focus on this here since it's an introductory lecture on visualization. So, and let's go over some techniques. Let's start easy with diagram technique. So we have simple 2D diagrams, so something that Excel would spit out, or numbers, or your favorite business talk, right? And let's start with the so-called scatter plot. It shows the correlation between variables and, well, all the stuff that I put down here. But what's a scatter plot? It's the stuff you did in, I don't know, 6th grade or 7th grade, okay? So here's a graph. Compute a few points and draw those points onto a piece of paper. So it sounds complicated, right? We make up all these fancy names like scatter plot matrix, whatever, all we got. But essentially, the basic idea is to draw points on a piece of paper, okay? And then if you want, you connect those dots and you get the function. So you all know what's going on here. The thing is just, the dots do not necessarily have to represent a function. So for instance, those dots here, there's obviously different y values for some x values, so they can't be a function. But it's really just you have a table of x and y values, for instance, such as this one here, and then I'll just draw those dots. Okay, easy. I'll let a computer do it. I get a result such as this one here. And I've also I put it on the slide, presented this in the intro as well, as a motivation that we can relate to this image here much better than to the left. Okay, so instead of glancing at those numbers, I can just glance at that one and see, okay, well, there's a linear relationship. Okay, and the same with this one here, or similar. If I plot that, I see, well, okay, that looks like a quadratic relationship, maybe with some clusters, and it looks like there's a few values missing, but that might be just due to the small amount of samples that I have. Okay, and then I might want to dig deeper into this. But the key point is that even something as simple as that, what you learn early on in high school, can be very powerful to distinguish, to characterize data, right? Here you can see, well, there's a linear relationship going up or going down. In particular, if you compare the topmost images like these two, well, it looks like it's in both cases linear, but there seems to be more of a spread here. So maybe that's just a cluster. So I have to look at more data. Same here. We got this sort of negative relationship between the two values, but it's relatively widely spread out. So maybe it's an artifact from an acquisition measurement simulation process. So maybe I need to dig into that deeper. So you can see two things. First of all, we're immensely good as humans to find these patterns, even without computer help. So computers can also find clusters, and we can use additional drawing techniques, analysis and drawing techniques, rendering techniques to highlight the clusters. But in many cases, actually, in particular for 2D data, it's not even necessary. We can do this automatically, and it's easy. Any child can do that, right? Any child can tell you that this goes top left probably before they attend kindergarten. Okay, so it's apparently an immensely simple task for us. So that's good. Hence, this is a visualization that is used pretty often. It tends to get harder when the data has more than 2 dimensions, right? If we draw this in 3D, we would have occlusion. If we draw this in 4D, well, we can't draw it in 4D, okay? So you see the problem. In 2D, it's fine, but as soon as you move to more dimension, you get into trouble. You have to then be more clever and go beyond elementary school. drawing techniques, and that's pretty much what InfoVis lectures are all about, what information visualization is all about, which we'll not cover here because we got a lot of stuff at our hands with SciVis already. Well, what else can we do? Well, if the numbers that we use, if say the 2D table has some sequential information in it, so for instance, x is time, okay, we can assume that time, well, it is quantized, but only at a sort of a quantum level, so never mind that. So time is pretty continuous, at least for our from our perspective. So it makes sense if I have 2 points to connect the in-between. Right, to say, well, if this is my revenue here and this is my revenue here, well, the penny went up, or this is temperature from here to here. So, I mean, the temperature didn't jump, right? It kind of went up. So when you have quantitative data over a scale that is continuous, it makes sense to, even though you might only have discrete points, to combine it. And as a matter of fact, what we're doing here, we're just doing linear interpolation. If we just combine every 2 points with the line, that's just a linear interpolation that I talked about before. You can also take more points into account, and then you get quadratic, cubic, whatever interpolation. But you need to be a little bit careful what to connect and what not to connect, right? If the x-axis is something that is discrete in nature, that doesn't have a continuous underlying phenomenon, you should not connect that. But you could, for instance, draw it as points, scatter plot, or if you want to see the quantitative details better, you could draw them as bars that just kind of rise from the bottom to the given point. And you can combine multiple bars, just like multiple lines, into one graph if you want to. So you would use a bar chart whenever, or it's in particular compared to a line chart, when those are discrete quantities and you don't want this continuous appearance. We already had a bar chart before, this histogram, right? That was, here you see the histogram of the image on the left, okay? And you see, if I zoom in, if I make this significantly bigger than I had it before for the transfer function, you can actually see that it's just a bar chart, right? And there are gaps in between, right? I mean, there aren't any values of a certain grayscale in the image on the left. So it's really the frequency, it's the number of occurrences of pixels of that grayscale image, of that grayscale value in the image. Okay, in that case, it doesn't make sense to connect this as a graph, right? So I have 10 pixels that are whatever 0.5 gray, and I have 20 pixels that are 0.6 gray, and I don't have any pixels in between. Okay, so it doesn't make any sense to connect those, so I draw them as a bar chart. I draw the histogram as a bar chart. Another very popular chart type is the pie chart. Here's the pie chart, right? And this is, as you can see, it's the relative numbers of native speakers in the major English-speaking countries in, well, before the dawn of the century. And as you can see here, I've kind of thrown all that, or a lot of what, in this case, numbers can do to make this look fancy, right? It's just a pie chart. What's a pie chart? It's generally a circle that represents 100% that I break down into parts. And I already covered the most important idea. You would use a pie chart when things sum up to a total to 100%, right? And then you can throw at it 3D and shading and make it less and less obvious and harder to see. You can add colors and all this. So I'm actually not claiming that this is a good visualization here to start with, right? I'm just saying you can do a lot of things to highlight certain areas or to just make it look more fancy, which surprisingly often makes the data harder to interpret, right? Why is this 3D? I don't know. Why is it tilted? I don't know. Why is it lit? No clue, except for it looks cool. However, there's one thing that you shouldn't underestimate. If something looks cool or looks nice or looks pleasant and doesn't, in the process, hide too much data, it might still be a good idea. Why? Because people look at it, okay? And you want to raise interest into a certain piece of information, right? Into a certain idea, into a certain concept. So while often I tend to depict this here as a little bit unscientific, it is not. So that should be taken into account, right? Just because you make something look more interesting doesn't mean you're not scientific. Just because it's not black and white and just because it's not 2D and looks ugly, it's not unscientific, right? So there's a lot of need for pleasant visualizations maybe not for the domain scientists. They don't care that much whether it's pleasant, but, or they don't admit, they actually do, but they don't admit. But if you want to convey something to the general public, right? If you want to convince something that, I don't know, vaccination is a good idea, if you want to convince something that global warming is happening, it might be a good idea to actually show it in a way that it doesn't like look ugly. Okay, so don't underestimate the importance of that when you design a visualization. Nonetheless, what else can we do? There's a ton of things that go along with pie charts. So for instance, I can display the values differently. I can pull them out, right? That potentially makes them easier to read. In particular, Canada here was white text on yellow background. It's probably hard to read. I might actually pull them out. Like in particular, if I have smaller pieces of the pie, I might want to pull them out. There's obviously a degree of freedom. I can rotate the things in any way, the thing in any way that I want. And when I did this here, I couldn't resist but add a few things to it. So that's probably the point where it kind of gets ridiculous. But again, remember my comments from before. So just because something is funny, if it still conveys the correct or the message that I tend to get across, right? If I intend to say, well, all Americans are bad because they're taking over the world, whatever, right? So then this might be a good idea. It's very, in particular, when you go kind of this far here, then it's very hard to kind of keep track. Is this still sort of reasonable what I'm doing here, or am I doing propaganda? And well, as a matter of fact, there's a lot of visualization folks that are hired to do propaganda, right? This might be your task at hand. But if you try to be sort of neutral and convey information in a still pleasant form, but be neutral and let the viewers decide, well, that might be a little bit over the top. Here's another example of a visualization that's not a pie chart. I actually grabbed that from a talk from slides from, if I remember correctly, it was Cisco or HP. I think it was Cisco, okay? And they were trying to make this point like Internet of Things grows by our hardware or routers or switches, whatever, it's important, okay? That was the point they were trying to get across. I've just redrawn this image, and what they were trying to show was basically a relation between human population and connected devices. And the point was, 2003, we had a few connected devices and a significantly larger population, and then 2020, or this has tipped somewhere around 2010, and now it's kind of opposite. And that visualization, I don't know what happened to the guy who did this, right? I mean, why would you potentially do this if you could just do it this way? So I took the same graph and I just plotted it myself. So this would be way better, right? I mean, it's just for so many reasons better, right? It's a continuous thing. Internet of Things grows continuously. Human population, well, not so grows continuously, but slower. And I can plot the data points to depict where did I interpolate in between. And this is just so much better. I can see where those two cross. And what you see here is that even people that do these visualizations for, well, for a living aren't necessarily doing it the best possible way. And there's two reasons for that. A is they don't know better, right? Sometimes I would say here, this is just plain bad. The color choice, I redid the image, but I used the original color. The color choice is terrible, right? So it's just bad in about pretty much any regard. It uses a two-dimensional metric area. We are really hard at judging area instead of just height. So it's bad in just about any metric that I can think of. So that's just dumb. Put it this way. But there's other situations where you again might want to get something across a little bit different than it probably is. And we would generally refer to that as propaganda. Okay, propaganda is happening really everywhere. It's surprising how much it happens around you, like literally every day. And there's interesting sessions. So when we do our visualization conference, visualization scientists, there's an annual conference called the IEEE Visualization. It's the main event. There's even a whole session dedicated to it. It's called VisLies, where people just over the year gather visualization stories, where they say, okay, well, this is a visualization that was on purpose done in a way that it's not inaccurate in a sense that it used the wrong data. I mean, that's the easiest way to lie, right? To just cheat when it comes to the data. Okay, so I don't know, 10,000 people died, and you say 1,000 died. Okay, so whatever. No, but you can just use the visualization to sort of lie, to hide the details. And that's not what we want to do here. I just mentioned that this is an important topic, and it might well be the whole purpose of your employment at some point, which is okay. I mean, you gotta figure out the ethics yourself. Okay, so but it's a thing that's important. Okay, so now let's get away from all that propaganda and other stuff, and let's look at other things that we can do. Let's look at a specific example because we'll need that later on. Let's look at height fields. I tend to look at height fields pretty often. Why? Because they're kind of the simple most data set that I can imagine in 2D. And it's even more simple. Let's start with 1D. Okay, so what do I mean with height field? I mean a scalar value. I mean, I assign to each point on the plane, or in 1D to each point on a line, I simply assign a single value to it. I mean, I can't really do less. I can't assign half a value, right? So that doesn't work, or 0. Well, I could, but it doesn't make any sense. Okay, so I want to start with just assigning one value, and that's what we call a scalar field. We'll later on see vector fields and even tensor fields if we get to this semester. Okay, so we can assign multiple quantities, but the easiest way is to just assign one quantity. Okay, and then we call it a scalar field. A 1D scalar field, we would generally call this a function plot. Okay, so we have one dimension, and each point along that one dimension gets a single value which we can draw as height. Okay, done. There's really not much more to say about this. It's a well-proven concept. We call this a curve. And well, it's no big deal. But nonetheless, it's a one-dimensional scalar field. Now, let's do the thing in 2D. So we have x and y, and we get a z value or a height value that depends on x and y. And even in that simple situation, you could say, well, okay, sure, I draw my plot in 2D, but it starts to get complicated, okay? So, because what we get is pretty much a surface. So here, that's a two-dimensional function, and it's already tricky when you think about this. Why? Because the result is a three-dimensional thing, right? It's a surface, but it's got three-dimensional structure, okay? So when I just focus on that one, I have to figure out some way how to draw this. Why? Because I do a projection in the end. My result is usually 2D. It's a piece of paper. It's a screen. And that screen, that piece of paper, whatever, is two-dimensional. Okay, so we run into trouble. What I did here was I've drawn the so-called wireframe representation. So instead of drawing the entire surface, I just drew a bunch of selected values across x and y, and I drew them as wireframe. And you can still see that there's trouble. Right, so we've got occlusion going on here. Is this back and front? I don't know. Kind of hard to tell. So let's get rid of the back. Okay, so the first thing you can do is you can do what's called the hidden line representation. So anything that's hidden, that's behind, will not draw those. Okay, so even though there are lines here, right, there should be lines there, I don't draw them, and it gives me a much better spatial perception here. I don't know what's front and back, but at the cost of losing data. I don't know what's going on here. So here, there might be something cool here, right? So there might be, I don't know, oscillation peaks, outliers, but they're completely hidden. So it's not all great. So how do I fix this? Well, I could add interactivity. Well, start to rotate the thing, generate a movie, give the scientists the possibility, the users, the possibility to rotate that and look at it from all directions. Okay? Then things get better. It's not perfect, though, when it comes to perception. I could add shading to it, right? I could pretend that there's an artificial light source, and I could compute a simple interaction between the surface and that light source. And that gives me more details. I could make things that are further away darker, right? So I could use shades of gray. What's the advantage of that one? Well, even more spatial perception, even better spatial perception. Still occlusion going on. I can rotate that. But I have to choose somehow. I have to choose a lighting model. Right? When I compute lighting, I have to say, okay, what lighting model is that? Should I pretend that it's clay, or should I pretend that it's metal, or should I pretend that this is plastic? Right? I mean, I have to figure out how should the light interact with it. I have to choose colors or grayscales. If I choose grayscale just to convey shape, I've lost the ability to use grayscale as a means to convey the values themselves. Right? I could make high values, I don't know, brighter than low values. Okay, but I can't anymore if I use that for conveying the shape. So you see there's pros and cons, and that even at the point where we have this very simple situation, just a height field. We already get occlusion, we get into trouble of choosing a lot of things that have nothing to do with the data. That's the important thing. So this lighting model has nothing to do with the data, right? If I pretend this is metal, if I color it, I don't know, in rainbow or whatever, this has nothing to do with the data. It doesn't depend on the data values directly. It's just my choice of where do I place a light source so that this surface is lit. And any of those choices are always very dangerous, right? So there's always the danger of making a mistake here and hiding things, okay? Or there's an opportunity for hiding things on purpose, okay? So there's always two sides to it. So, but let's again step back from those problems and look at what was my input here to start with. I said it's just a two-dimensional scalar field, and I've drawn this as a height field. So the funny thing is, and that happens a lot when I do oral exams, is I ask students, okay, you have a two-dimensional scalar field, what would you call that? And generally when I ask this question on an exam, like students are going like, what the fuck? I don't have a clue what he's asking. The funny thing is, even though I explained this to you, it'll still work in the oral exams. But I often get this like literally like what's he trying to say? And I'm okay, and then I generally go on and then I say, well, okay, I said this in lecture, you probably don't remember, but whatever. So just imagine you have a two-dimensional scalar field. You generally wouldn't refer to that as a two-dimensional scalar field, okay? So say you attend this lecture here, and you talk to your boyfriend, okay? So I'm pretty sure you've talked to your boyfriend or girlfriend about two-dimensional scalar fields already, but you would never call them this way unless he or she also attends the lecture and you're a little bit geeky. But other than that, you wouldn't refer to them. Like, how would you call a two-dimensional scalar field? Think about it for a second. How would you refer to that? There's a very intuitive name that you've all used in your life, I guess. What's the two-dimensional scalar field really? Feel free to use the chat. That's what the whole Twitch thing is good for. Okay, no idea? Works just as well in the oral exam. Okay, that's gonna be fun. Okay, no. What is a two-dimensional scalar field? Well, it's a black and white image. That's it, or a grayscale image. Right? So a picture, a black and white picture, is a two-dimensional scalar field. That's it. Right? Take a black and white image. But again, it's usually a grayscale image, what we call a black and white image. Like a black and white image is a scalar field, it's a two-dimensional scalar field. It assigns a single value to every point in 2D space within our domain. And we just, how do we visualize it? Well, we color code it. Well, the color is pretty boring. It's between black and white, right? 1 is white, 0 is usually black. But that's a very typical thing. So if I give you a 2D scalar field, right? The first and most intuitive visualization is just kind of draw it as it is, but you can't draw it as it is. You have to do some mapping, but the mapping is really take every value as a single pixel and assign a transfer function, a color to it from 0, black, to 1 white, and interpolate in between. That's it. Right? I mean, the implementation requires you to do all of these steps, do a transfer function, but it's very intuitive. So you want to draw it as this one here. In particular, if you take an actual photograph, right? I don't know, the photograph that I had before of the clown in front of the mirror, if you would draw that as a height field, it would look like a crazy mess, right? But if it's something that is somewhat smoother, I could draw it as this one, but I might as well draw it as just a grayscale image, right? What's the advantage of that? Well, there's a giant advantage of that one. No occlusion going on, right? So this part here would be bright, this would be dark, and I would look at this from the top, right? No occlusion going on. I see all the values. I see anything that's, there's nothing behind whatever certain areas, right? So that's good. So think about simple things. Well, I guess the chat is working. Well, it's early in the morning, right? I mean, it's before 12 o'clock. No, it's normal. Also in presence lectures, there's very little participation, unfortunately. Okay, so what else can we say? Okay, again, two-dimensional data sets generally just pictures, and that's it. Even if there's 2D vector data, okay? So here's another question along the same lines. You have a 2D data set, okay? And it's a three-dimensional vector field. How would you call that? Okay, that's a color photograph. Okay, it's a color photograph. Okay, so no big deal. But let's now look at other ways to visualize them. So just keep that in mind, even though I don't have a slide on it. Okay, so don't learn for the art exam from the slides. Learn from my lectures. Okay, because sometimes I'm this nasty professor that doesn't do slides on certain things just to check whether you actually attended the lecture. Okay, so the first thing is draw it as a picture, like literally. In particular, when we talk about scalar fields, right? Just draw them as a picture. Just draw low values as dark, high values as bright. Look at them, see if it works. Another opportunity is draw them as geometry, right? What else can we do? And that's the last thing that I want to talk about today. We can draw isolines. Like, what the hell are isolines? Well, those are lines that are isometric, that follow certain values that remain unchanged. Okay, so we can pick, that's an important thing to draw isoline. We pick a certain value, say 42, and then we check where does 42 show up in our data set, which would give us a bunch of points. But what I don't want to just draw those points. I want to connect those points with a line. I want again to recover the continuous property of that value. Okay, so I want to connect this as a line. Have you seen that before? Of course you've seen that before. I'm pretty sure you looked at maps before. Right? I assume that each and every one of you has seen a map before, in particular a topographic map, such as this one here, which draws a scalar field, a height field, draws that as geometry. But on top of it, draws these lines here. What are those lines? Those are isolines. Those are lines that correspond to certain heights. Okay, so every point along this line here has the same elevation. Okay, and that's what we call an isoline. Okay. We can do this on maps. We can also do this in volumes. Okay, here's the whole volume. No, it's not. The question is an isoline based on a distance. Let's maybe go back to this one here. Well, technically you could say yes. It's the distance to normal, 0, right? But in general, I would say no. It's not necessarily based on distance. It's based on the values. It's a local quantity. So an isoline, whether an isoline is at a point or not, is a local quantity. It just depends on that point. It's just highlighting points that have something in common. Okay, take this, oops, wrong button here. Take this isoline, for instance, this one I can read. It says 7,400. So I guess that's 7,000, let's see, where's that? Emerald State, so that must be foot. So it's 7,400 foot in height. So you could say it's a distance to the bottom, to 0 level, but it's a distance because if you have that notion, this is a distance data set, right? It's based on the height field. It's based on the local quantity. So generally, I would say no, no distance here. It's just those are all the points that have height 7,500 foot, 400 foot. Sorry. Okay. So the question is, how do we compute those lines? Okay. Or here's another example before I get to the computation. Here's another example of taking a three-dimensional data set, which would create isosurfaces. If we move one step up, we have a three-dimensional scalar field. We're interested in an iso structure. That would be a surface. But I can again do a clipping. Right? I do a selection operation here. I clip the data set and I select just a plane out of it. Okay. So if I select just a plane out of it, I get isolines, and in this case, those are pressure isolines. Here's another example of a clipping approach with a selection on the clipping planes. Okay, and I can again draw isolines, which are cross-sectioned through the isosurface. So now the question is, how do we compute those isolines? So they're apparently an important thing, otherwise I wouldn't mention them here. They're often used in meteorology, topological maps, in a lot of other cases as well. How do we compute them? And there's an approach to that that's called marching squares. It's a relatively simple, super efficient approach to compute those isolines. Okay, as a matter of fact, we'll also do that in the exercises, so you'll have the chance to implement that firsthand, and it's pretty easy. It's a divide and conquer approach, meaning it takes the data set and breaks it up into grid cells and processes each cell independently. Okay, so this is also why it's so simple, because we don't need to consider the entire data set, just a small portion of it. So let's look at this cell here. Remember again, a cell is the structure in between the sample points. So if I have 2D Cartesian grid, pixel grid for instance, then those are my values, say height values or grayscale values for that photograph. And this is the cell in between. So I won't consider every point, I will consider every cell, which means 4 points if I have a Cartesian grid. So, what do you say? So, and that's why it's also called marching squares, because those are squares and we march over the squares. So, the first important thing, we need to have some sort of an ISO value. So that's an input parameter. This approach takes two input parameters. One is the dataset itself. Obviously, without dataset, we can't compute anything. And second, we take an ISO value. Like, what ISO line do I want to extract? So this is something I have to choose. Okay, so once I've chosen then, what do I need to do? Well, I run over each square separately. And the cool thing about it is once I combine the information for each and every square into like the final image, I get a complete image. I don't miss anything. So it's a greedy approach, but that's working. It's accurate in a sense that I don't lose any ISO lines. And that's kind of a cool thing. If I can break problem down into smaller problems, reassemble the result, and voila, I get a correct answer. This doesn't always happen, but here it happens. So how does it work? It's, as I said, it's a pretty simple process. So we take our grid and we take our ISO value. Again, very important, we need to have that ISO value, otherwise we can't do anything. That, by the way, is another typical question that I ask in an oral exam is, I give the students a grid and say, compute the ISO value, and they start to do things, and then after 5 minutes I say, well, you're not getting anywhere, right? And they're like, no, something's wrong here. And I said, well, sure, I haven't given you the ISO value yet. Why did you even start? Okay, so important, we also need an ISO value, otherwise there's nothing we can compute. So what do we start with? Well, we first start with a simple classification. We take our cell, again, I said we start cell by cell. So we take this cell here, for instance, and what we do is we simply look at, is the cell vertex, and there are 4 of those, are those cell vertices above or below, and maybe below equal, never mind the equal here, whether they're above or below the given ISO value. So what does that mean? Say I have 5, 20, 25, 30 here as values. So those happen to be my values. And I give you an ISO value of, say, 6. Well, 5 is below, I think I said 20 here, 20 is above, and so on and so forth. So it's a simple Boolean value that I compute, okay? Whether I'm below or above equal. And that classification I do for each cell separately. Here I did it for the entire grid because it's so simple, but again, we only consider a cell. Okay, so in this case, I apparently had 1 below, 1 above, 1 below, 1 below, so total 3 below, 1 above. So that was the result of the classification of that cell. And then I just look at this classification. And now the cool thing is I can derive pretty much everything from this simple classification. Because what happens? Well, if all my values are above or below the ISO value, there's no line passing through it. Right? I mean, it's easy if you think about a height field for a second, right? If I say I want to have the line that corresponds to, I don't know, 500 meters, and this is 10 kilometers, 9 kilometers, 8 kilometers, 10 kilometers, we're apparently on Mars, then, well, this is way above my ISO line, so no reason to consider it even. And the same is true if we're below, okay? So, fine. Now, what happens in a situation where we have some below and some above? Well, if, for instance, here, the top right is below and the other 3 are above, then we must have a transition from below to above somewhere in between. And the cool thing about this approach is we only consider the edges here. I only consider what's going on this edge here, or what's going on this edge here. And that tells me, is there a change in this Boolean value or sign? I could also call it plus or minus, true or false, 0 or 1, whatever suits you best. Okay, so here I call those plus and minus. So if I have a change in classification, I know that somewhere along this line, something must happen. Okay, and here as well. And I can just connect those 2 points. So what I get out of the classification is an answer on what lines something is going on. I don't know where exactly on the line, but I know what, I know that something is going on. I know nothing is going on this line, nothing is going on this line, but I've got something going on here and something going on here. So somewhere along that line, I have a point, somewhere along this line, I have another point where the line crosses the cell boundary. And if I would know those points, I could just connect them with the line. Here's another example. What can happen? I can have two pluses or two minuses. And there's not really much that can happen. Either they're all plus or minus, nothing to do. One is plus or minus, this situation here. Two are plus or minus, and the two are adjacent, this situation here. Well, obviously you have rotated versions of that. So what else can happen? Well, three, well, no, three is this one here. It's just a different way of looking at it. Go away. Almost done. So that seems to be. So what else can happen? So 3 isn't a special case, right? And 4 is also not a special case. It's the same as 0. So, so what we need to look at is this case where we have 2, but they are what's called kitty corners. So they're on different opposing sides, because then we have a problem. We might want to connect this way or that way. So we don't know whether this situation or that situation here, okay? So what we have to do, so what's left before we can draw the lines and then proceed to the next square are two things. So two ingredients are still missing, and then you know everything you need to know about marching squares. The first ingredient is, how do I find the exact point? And that is independent of whether it's one of those ambiguous cases or not, because the point is just based on a decision made on the edge, and the edge doesn't care what's going on. Okay, so question 1 is, how do I find the intersection point? And question 2 is, if I happen to have such a case here where I've got the kitty corner configuration, I have to figure out whether I want to draw it this way or that way. Once I've figured out these two things, where are the points for all cases, and how do I resolve this ambiguity? I just draw and proceed to the next square, do this for all squares, and I'm done. And those two things are, I leave open for next week. So next week we will start this stream here with me answering these two questions. How do I figure out the points, and how do I, if and only if I'm in this situation here, because then I'm not done, how do I figure out which of the two configurations to draw? And then you got your isolines. Okay, so that's it for today's stream, unless you have any questions. So there's still time for questions. Oh, we got a total of 4 messages in the chat in 1.5 hours. That is not much. So are there any questions? As usual, attend the exercise, do the homework. And this year will be a homework as well, so to do this isoline stuff. Well, sure, that's fine. Just watch the video on demand, and you'll get the rest, and then maybe a question pops up. Okay, so it's fine. Then that's it for today, and as usual, stay healthy. Bye-bye. See you on one of the next streams. That's either next week in this, or that's any of the other streams, and there's a summary of the streams coming up in a second. Again, bye-bye. Stay healthy.